next talk will be Hypra, a deductive program verifier for Hyper logic, and the presenter is Anqi Lee.
So hello everyone, I'm Anqi, and today I'm here to present to you our deductive program verifier, which is called Hypra. So the motivation of our work is to verify hyperproperties, which are properties over multiple executions of the same program. So a type of hyperproperties is hypersafety properties, which we call for all plus because they universally quantify over program executions. And an example for this is determinism, which says that for any two executions, if they have the same inputs, then they also have the same outputs. Another type of hyperproperties is exist plus, and these are useful for proving the existence of bugs. And an example is the negation of determinism, which is useful for proving the violation of determinism. Moreover, we have for all plus, exist plus hyperproperties, and an example for this is an important security property, which is generalized non-interference, that is GNI. And this property basically says that for any two executions, there exists a third execution such that it's related to these first two executions in a certain way. And moreover, we have exist plus for all plus hyperproperties. And an example is the negation of GNI, which is useful for proving the violation of GNI. And another example of this is the existence of a minimum, which says that there exists an execution such that its output is smaller than the outputs of all other executions. And of course, all these different types of hyperproperties can be mixed together to form useful hyperproperties. And to automatically verify these hyperproperties, many verifiers have been developed. And as you can see on the slide here, there are no existing verifiers that can handle all the hyperproperties that have been listed here. And moreover, the existing verifiers are limited to a fixed quantification scheme. This motivates us to propose an automated verifier that can handle all the listed hyperproperties and mix different types of them in the proofs. So to be more precise, the goal of our work is to build a deductive program verifier that can automatically verify arbitrary hyperproperties. To do so, we automate a program logic called Hoare logic that can prove and disprove arbitrary hyperproperties. But before I go into what Hoare logic is, I would like to quickly revisit Hoare logic. So as you all know, Hoare logic uses Hoare triples of the form PCQ, where P and Q are the pre and post conditions respectively, and C is the program command. Here, the pre and post conditions P and Q, they are predicates over states. In comparison, Hoare logic uses hypertriples PCQ, but the P and Q here, they are no longer predicates over states, but predicates over sets of states. So a hypertriple PCQ holds if and only if executing C in any set of initial states satisfying P results in a set of final states satisfying Q. So these assertions that are predicates over sets of states, we call them hyperassertions. And because of the existence of hyperassertions, we can now explicitly quantify over the states in the set with universal and existential quantifiers. So to give you a little bit more intuition on this, I'd like to go over a very simple example. So in this program, we simply assign the input to its output. And we want to verify that this program is deterministic. So by the definition of determinism, we can easily come up with the pre and preconditions that I show on the slides here in green. In particular, these pre and post conditions, they are hyperassertions. And in these hyperassertions, we consistently use sigma and sigma prime to represent an initial state and a final state respectively, and we use S and S prime to represent a set of initial states and a set of final states respectively. So now that we have learned about Hoare logic, let's move on to how we build a verifier to automate it. So on a high level, the verifier we build is called Hypra, and it takes an input program with specifications. And if this program satisfies its specifications, Hypra is going to output yes, meaning that verification succeeds. Otherwise, it's going to output maybe not. And in our actual implementation, instead of letting Hypra directly compute the verification result, we actually let Hypra generate a Viper program that encodes the semantics of the input program as output. So Viper is an SMT-based intermediate verification language that is already automated. This means that as long as Hypra can automatically translate the input program to a Viper program that encodes the input program semantics, then we can automatically obtain the verification result. However, this approach presents two major challenges. The first one is how can we design a Viper encoding that tracks an unbounded number of executions, which is what we need to do when reasoning with Hyper-Hoare logic. And even if we have come up with such an encoding, it might not work well in practice because of the practical limitations of SMT solvers, which we will get into later. Then in this case, how can we make the Viper encoding that we design work well with SMT solvers in practice? So for the rest of the talk, we will focus on how we solve these two challenges. To tackle the first challenge, given an input program with specifications that look like this, we will generate a Viper program as follows. So here we will first declare a variable S to represent a set of initial states. And this set is assumed to satisfy the precondition P provided by the user. Now, because the goal of the Viper program is to encode a set of final states that are reachable by executing the command C in an arbitrary initial state in S, this tells us that apparently we need another variable, which is S prime, to represent this set that we want to encode. So for the rest of the in the rest of the Viper program, basically we will constrain what states are in S prime based on what states are in S and also the semantics of the program C. And of course, in the end, we need to check if this set of final states that are reachable satisfy the postcondition Q provided by the user or not via an assert statement. So to see how we actually constrain S prime based on S and C, let's look at an example where C is a simple assignment. So here we assign the constant 5 to variable X. So in the encoding, first we say that for any initial state, sigma, that is in S, it must reach some state in S prime. And this state in S prime is basically sigma, but with X updated to 5. So this line of code tells us that now all the reachable states will be in S prime. But this does not mean that all the states in S prime are indeed reachable. But because we want S prime to be the exact set of reachable states, this tells us that we now need to constrain S prime further by saying that for every state sigma prime in S prime, it must be reachable from some initial state sigma that is in S. And sigma prime is reachable from the sigma by executing this assignment in sigma. So with the assignment encoded in this way, let's see how we can prove a postcondition. So the postcondition you see here is a conjunction of a for all plus property and an exist plus property. And to prove the first conjunct, which is a for all plus property, the information we need is the property that all the states in S prime must satisfy. And notice that this information is available in the second half of the encoding, which is line 3. In comparison, to verify that the exist plus property, the information we need is the property that a state needs to satisfy in order to be in S prime. And this information is available in the first half of the encoding, which is line 2. Now, if we can encode every single program command in the way we encode this assignment by using S and S prime being two potentially infinite sets of states, then we can track an unbounded number of program executions, which solves our challenge number 1. But the bad news is that the Vyper encoding that looks like this doesn't work well with SMT solvers in practice, which brings us to our challenge number 2. Before I bring up the solution of challenge 2, it's important for us to know why such a challenge even exists. And to understand this, we first need to know something called e-matching, which is a mechanism that used by SMT solvers to instantiate quantifiers. So in e-matching, every universal quantifier is associated with a syntactic matching pattern called trigger. So imagine that you have this assumption here, which says that for all x, f of x equals to 2 times x. Then this universal quantifier is associated with this trigger that says f of x. Now imagine that given this assumption, we now want to prove an assertion which is f of 10 equals 20. When the SMT solver sees the term f of 10 in this assertion, it's going to see that this term syntactically matches the trigger f of x. So it will instantiate the universal quantifier with x being 10. Now this instantiation immediately tells us that f of 10 equals 2 times 10, which is 20, thus allowing us to prove the assertion. Now imagine a slightly different situation, like where we want to prove the exact same assertion, but with a slightly different assumption. And this assumption says that for all x, f of x equals f of 2x. Now, when the SMT solver sees the term f of 10, what happened before is going to happen again, meaning that the universal quantifier gets instantiated again with x equals to 10. But now this instantiation produces a new term, which is f of 20. And you can easily observe that f of 20, once again, syntactically matches the trigger f of x. So this will cause the universal quantifier in the assumption here be instantiated again. And at this point, it should be clear, it shouldn't be hard for people to see that at this point, the quantifier will actually get stuck in an infinite loop of quantifier instantiations. And this is known as the matching loop problem. And it will cause the SMT solver to diverge and not return any result. And this is exactly the reason why our Vyper encoding that we just saw wouldn't work in practice. So recall that this is the Vyper encoding that we just saw. Let's do the analysis again to see why there's a matching loop here. So imagine the first universal quantifier gets instantiated in some way, and then it will produce a new term which says that some state in S prime. And this, of course, syntactically matches the trigger of the second universal quantifier. So the second universal quantifier gets instantiated and produces a new term, sigma in S. And this, apparently, syntactically matches the trigger of the first universal quantifier. So it's going to instantiate it again, and the whole instantiation process that we just went over is going to happen again and again and again. So this is a matching loop. Now that we have identified the problem, how can we solve it? The answer is now instead of tracking only one set of reachable states, we track an upper bound and the lower bound of it separately. So to apply this solution to our original encoding, now the S prime in the first half of the encoding will be replaced by S prime exist, while the S prime in the second half of the encoding will be replaced by S prime for all. This solves the matching loop problem because now if the first universal quantifier gets instantiated, the new term that it produces is some state in S prime exist, which does not syntactically match the trigger of the second universal quantifier, which is some state in S prime for all. Thus eliminating the matching loop that we just saw. But now that we don't have matching loops anymore, some people might wonder if we are still able to prove the properties that we were able to prove before. And the answer is yes, because given a prose condition, such as the one that we see here on the slide, for every occurrence of S prime, we will replace it with S prime for all or S prime exist, depending on the type of hyperproperties that we're proving in the post condition. So this solves our challenge number 2. So this is the high-level idea of our approach. To demonstrate that our approach actually does work in practice, we have evaluated Hypra using 84 different programs that are adapted from the benchmarks of existing verifiers. And this table here summarizes our evaluation result. And as you can see, Hypra can indeed verify arbitrary hyperproperties within a reasonable time limit. And in fact, for 93% of the benchmarks, Hypra can finish verification within 5 seconds. Moreover, in general, Hypra only need a very modest amount of proof annotations provided by the users to finish verification. So to sum up, in this work, we have built an automated deductive program verifier that automates Hyper Hoare logic, where the assertions are predicates over sets of states. And we do so by generating Viper encodings that track sets of states, and also by tracking an upper bound and the lower bound of the set of reachable states separately. And of course, there are still many aspects about Hypra that we didn't have the time to cover in this talk. For example, Hypra can reason about errors, meaning that it can prove and disprove the existence of runtime errors. It can also reason about loops using 4 different loop rules, which includes a novel loop rule for all star exist star hyperproperties. So if you're interested in learning more about Hypra, please feel free to read our paper. So this completes my talk, and thank you very much for your attention.
Questions? Yes. I was just getting the mic to work.
Thank you so much for the talk. Really, really nice work and really nice presentation.
Thank you.
Something that you might or might not have considered, but I'm curious about your idea. So what if you have not a single program in the middle, but let's say a family of indexed different programs? What the encoding into unary specification in Viper would look like in this case?
I'm not sure if I understand the question correctly. Are you asking, like, what if we want to verify properties for different programs?
That's right. So
yes.
see, like, I might be wrong, but Descartes, the Cartesian Hoare logic,
Yes.
I
yes.
think they actually do consider triples with different programs, of like 2 or 3 different programs.
Yeah, thank you for your question. I didn't, like the hyperproperties, as you see on the motivation slide, we define it over properties over multiple executions of the same program. So when we're designing Hypra, our motivation does not include verifying hyperproperties that relate multiple programs. But it is definitely something that's worth considering with adding to Hypra. And I want to specify that although Hypra is not designed to verify this type of properties, we can technically encode it in a certain way as a Hypra program. So for example, if you have 2 programs, P1 and P2, what you can do in Hypra is that you have a if condition and then put P1 in the if branch and then P2 in the else branch. So this is one way you can encode it into Hypra. But as I said, we do not design this tool for this kind of properties. So I'm actually not sure if it will work well if the program contains loops, because that is the trickier case. Yeah, exactly. So so I think we can technically encode encode the programs like that to verify properties over multiple programs. But it probably wouldn't work well if the programs have loops.
One more question there.
Hi, thank you for the talk. I really liked it. I had a question about your use of upper and lower bounds to describe the set of states. So what you end up with, I suppose, then is you know that S prime lies in this interval between S prime exists and S prime for all.
Right.
Can you give us some idea of whether that sort of imprecision from knowing exactly S prime weakens your ability to reason about certain kinds of properties, and if so, what kind?
Yeah, thank you so much for the question. It's actually a very good question. We didn't specify which one is lower bound, which one is upper bound, because it might cause some unnecessary confusion, which is not something that we want to get into on this slide. But actually, S prime exist is the upper bound, and S prime for all is the lower bound. Because for the first encoding, you say that all the reachable states are in S prime exist, but S prime exists, but not all the states in S prime exist are reachable. So this tells you that clearly this is an upper bound of S prime. So now you might wonder, is this really sound? Because if you prove that some state is in S prime exist, because it's an upper bound, it might not exist in S prime, which is what we actually want to prove. But the thing is that if the Viper program verifies, what we are able to prove is that for every S prime exists, that is a superset of S prime. In particular, when the S prime exists is exactly S prime, this property satisfies. So, yeah, even if it's an upper bound, but because it's like for all instances, that's a superset, that's what we're proving, so it's actually sound. So for the S prime for all, it's similar, but just the other way around, a lower bound. But eventually you can pick the S prime for all that is exactly S prime to convince yourself that it's sound.
Okay, one very quick question. Can you pass the mic to him?
Thanks for the fantastic talk. You said arbitrary hyperproperty. What about arbitrary quantifier alternation? Because you showed exist for all exist. Can you do for all exist for all?
For all exist for all? I think theoretically, yes. And actually, I can't recall correctly if there is an example like that in our benchmark, but I do believe that, yes, we can do that. But I have to run it on a concrete example in order to give you like a definite answer. My guess is that, yes, we can, but we might run into problems with triggers, which is something that I talked about. Yeah, and it's definitely one thing that we need to think more about. Yeah, but yeah, I don't think I can give you a definitive answer, but my guess is yes. Maybe with some limitations on trigger that could be solved. Yeah.
Okay, cool. Thanks a lot.
Sounds like a good conversation for after the session. I'll let you guys move on with that. Okay, let's move to the next speaker now then.